So what we've seen so far is that we generally require an infinite bandwidth to form an actual signal, but when we are transmitting or receiving signals, we only need, let's say, the first spectral components, especially if we're doing digital modulation. We are representing a signal by its digitalized form, so by zeros and ones, and we can represent signals just as square impulses or rectangular impulses. The question is, if we have a general signal and if we want to cut its, let's say, its spectrum, if we want to restrict its spectrum in such a way that we can still restore it, we can still get the signal well enough, but we don't want to have the full spectrum that is, in the general sense, infinite. How do we do this? So how do we cut out spectrum, and how do we keep what we've said previously? How do we restrict the spectrum in such a way that we can still restore a signal, but generally we only keep its main components? So ideally, what we would have, just as an example, we remember the rectangular impulse. Let's say we have a periodic rectangular impulse. Remember that we had this sine x over x type of function, so oscillating with a maximum and the minimal though, and we have infinitely many spectral components, but we can actually restore such a signal only by its central, which is the DC component, and the two largest frequency components. So two frequency components on the two sides of the spectrum. How can we do this? How can we restore the signal, and how can we, first of all, how can we restrict it in such a way as to only transmit those components? Well, ideally we would cut everything else. So this is the response we would want ideally, what you see on the slide. Essentially we only leave the central components and everything else becomes zero. So we cut out all the rest of the signal. However, if we have an analog signal, how can we do this generally? So we have some time domain signal, we are not directly manipulating its spectrum, so how can we get such a result? Well, the answer is by applying filters. Now, a filter, of course, depending on the realization, it might be an analog, it might be a digital thing, so it might be computer-based, but these filters should generally give us exactly this behavior we need. So they should ideally be a function which we can convolve, which we can pass through with our original signal, combine with our original signal in such a way that ideally they only leave intact the portion of our signal in frequency domain which we need and remove everything else. So if we want a signal which essentially acts like a rectangle in terms of the frequencies, so it leaves a set of frequencies intact and cuts everything else, in terms of the time domain, this filter would look like, again, the inverse Fourier transform of the rectangle is sine x over x. So the filter in time domain would look like the spectrum of a rectangular signal in the frequency domain. So it may look a bit weird, but essentially the idea is that a perfect filter would have a time response which is exactly like the spectral composition of a rectangular filter. Now this is, however, hard to realize. You see this time characteristic, if we convolve it, if we combine it with one of our signals in order to cut the spectral components higher than a specific frequency, we can have a lot of interference. We can have a lot of intersymbol noises, because if we want to apply this to, let's say, many bits, because for each rectangular signal we have, which represents a bit for us, we might want to do such a restriction. What we're going to get is actually those sine functions interfering with each other. So the time domain sine functions, unless they're very precisely placed in such a way that apart from the central maximums, all of the secondary maximums and minimums, they compensate each other and they, let's say, destroy each other. Unless it's very precisely calibrated to do so, we're going to have intersymbol interference and we're going to have additional noise. And what is more, it's very hard to make such a steep filter. So it's very hard to actually get, ideally, the derivative is a delta function. So it changes infinitely quickly. You can see on the rectangle, so it's a constant 1 and all of a sudden it's a constant 0. So in practice, this is not very easy to realize. This ideal type of filter is not that easy to use, and it should be very precisely calibrated even if it was ideally manageable. So what is used is a smoothly changing signal. And one of the top favorites is actually the Gaussian. So we said something about a Gaussian signal previously, but what about the Gaussian filter? Well, it's the same idea. So you use the Gaussian function this time, which we know it looks like a bell curve, essentially. It has a central maximum in which it has its highest value, and then it smoothly falls off within several sigmas, which are parameters of the function, and goes pretty much to zero very quickly. So the idea is that the very nice property of the Gaussian is that a Fourier transformation of a Gaussian signal is again a Gaussian signal. So the spectral and the time domain looks of a Gaussian signal are pretty much again Gaussians, just not the same Gaussians, but related in somehow. So the idea is that if we have a time signal, which is a Gaussian, we're also going to get a frequency signal, which is Gaussian. So the good thing is that if we convolve a Gaussian in time, we're actually going to get a convolution in frequency. And we can use this Gaussian to smoothly cut out and reduce the higher frequency harmonics, and then by using a similar procedure, restore those higher frequency harmonics which are within the range. So this is a very nice and favorite filter. This is a very nice, let's say nicely used filter, and you're going to encounter it in a lot of communications. And another very popular one is the cosine squared filter, which, as the name suggests, uses the square of the cosine function, which again, it looks roughly like a Gaussian around the centrum, but we will not really go into detail of that one. So the important thing to remember is that in this way, you can actually restrict your spectrum and you can reduce the contribution of the higher frequency harmonics which you do not want, and then restore them and essentially use this restriction to transmit at a more manageable bandwidth with a more manageable speed. So one last thing which I would like to mention, which we didn't have time for, is that all of these methods for forming signals, which we previously encountered, can be done smoothly. So what we saw previously for the digital signals, for the FSK, ASK, and BPSK, is that we have jump changes based on the bits. We can do the same realization of both ASK, FSK, and BPSK, and all of the other modulations by smoothly varying. So over a small, let's say, period of time, smoothly varying either the amplitude, the frequency, or the phase. And these types of modulations, again, they have their preference, and they are also used. And a combination of these modulations, either of them, with a combination of a filter, really grants you the capability of truly sending, emitting, and receiving any signal, any baseband signal in pretty much any frequency range you would like. As long as you have, of course, the required bandwidth, which again can be calculated knowing your type of modulation and knowing your transmission rate.